Now, the question that we ask is it the only optimization that you can bring? Are there any other optimization that are possible in this structure? The answer is yes, and that brings us to the discussion of what we call as the multi-bit trie, where the notion of matching more than one bit is taken and then streamlined, and I am trying to alter the data structure little bit, and in each iteration when I do the reference, I am going to match a fixed number of the bits. Remember, in the previous case, when I am trying to match, the multiple bits are matched only when there is the skip value and the segment I got some numbers into the more precisely greater than 0. Other than that, only one bit is actually getting matched. So, for example, here and here you are actually doing only one bit match. So, that I am going to extend by having a structure with the fixed number of the bits are matched at every iteration. So, let us motivate how this is actually done and what exactly the data structure look like and what is the performance of that with an example. So, let us try to take this set of the prefixes. As usual, P1 has got these the default route star, and P2 is let us say 0 0 star, and P3 is 1 1 star, and P4 is 1 1 1 0 star, and P5 is 1 1 1 1 star, and P6 is 1 1 1 1 0 star, and P7 is 1 1 1 0 0 star. So, these are the set of the prefixes that I got, basically 7 of them, and now I want to construct an optimized structure where more than one bit. So, let us say I am going to match 2 bits at a time. Every iteration I am going to match at least 2 bits. When I traverse from point x to y, I am going to match 2 bits. If I decide to go with the 3 length, then every label is going to indicate the 3 bit comparison. So, now how do I actually do this? So, the way to do it is, let us try to construct the structure, data structure, multi-bit trie structure for taking, let us say I am going to match 2 bits in every iteration. So, I am going to have a table which is looking something like this, and it has got 4 entries. So, 0 0 is one possibility, 0 1 is a possibility, 1 0 possibility, 1 1, and I am going to write in this one what prefix is actually going to be matched for these values. So, for example, if I get an IP address which is starting with let us say 0 0 0, this is adding. What I am going to do, this is the destination IP address, there is something else beyond this. I am going to take the first 2 bits and go to this table and ask what is the, given these 2 bits, what is the best prefix match that I can find from among these 7 of them 0 0. So, there is one which is P2, it is saying 0 0 star, there are 2 of them, P1 is also matched, that is star is anyway going to match, P2 is going to match because it is starting with 0 star, and P3 is not matched because it is starting with 1 1 star. So, that is not a case. You have got these 2 possibilities, either P2 or P1, and given the how the routing is done, the best match and the longest prefix that match, that is going to take the priority over the other things. So, in a nutshell, what I am trying to tell is P1 is actually a superset of prefix P2. Whatever P1 includes, it includes 0, it includes 1, it includes 0 0, it includes everything is matched. P2 is actually a subset of that. So, whatever is the best is P2 is the best, then I am going to take the on that. Now, P1 is not having a prefix of length 2, P2 and P3 have got a length of 2. So, I can match. So, every time something starts with the 0 0, I can actually go and directly say that P2 is the best match. Every time the destination IP address starts with 1 1, I might say that P3 is the best match on a similar note, and now anything which is starting with 0 1, anything that is starting 1 0, we do not know. So, that will actually the best match that I can find for these two is the P1. So, I write P1 here and then P1 here. So, one way to think of this is I am going to first consider all the prefixes of length up to length 2, whatever is there, and then if something is not having length 2, then I am going to expand that. So, for example, P1 going to include the 0 0 case, 0 1 case, 1 0 case and 1 1, all of these are actually matched, but among them P2 is actually matching 0 0. I am going to strike out to P 0 0 from P1's case, and P3 is matching 1 1, and I am going to strike out 1 1 from this set, and then for the remaining cases I am going to write P1 as the one. So, this is the prefix, this column indicate the prefix, the best prefix for those two bits that is matched, and the next column in this case in this table indicates the pointer. So, remember there are some more prefixes which are longer than of length 2, we need to accommodate all of them. So, the way to do it is, if any of the prefixes which are of length more than 2 bits here, that I am going to have it in the second level structure. One level structure 2 bits case is done. So, if your the match is only 2 bits, then at the first level I am going to complete, and if the other prefixes which are of length greater than 2, then I need to accommodate at the second level. So, in order to do that, what we do is we are going to find out if any of the prefixes which are up to length 2 are a superset of the other prefixes which are of the length greater than 2. In this case 1 1 star is actually superset of P4 which is 111 0 star, which is also a superset of P5 which is 4 times 1 followed by a star, and similarly P6 and P7. So, in effect P3 is actually superset of P4, P5, P6 and P7. It includes everything that P4 includes, it matches everything that P5 and so forth. So, in order to do that, what I am going to do is I am going to have a pointer from this location to the next level, and again I am going to match 2 bits in this case. So, one for the 0 0 case and second for the 0 1 and 1 0 and 1 1. These are the again 4 possibilities. Now, look for those prefixes which are of the length 4 or less than that I am going to accommodate here, in this case P4 and P5. So, 1 1, since P3 is a prefix of P4 and P5, 2 bits are matched here, and the next case is the next 2 bits 1 1 is matched, this 1 0 I need to find out, 1 0 1 1 followed by 1 0 is where, here it is, here I am going to write that this is the case of P4, and 1 1 followed by 1 1, 2 1s are matched here and the second 2 1s is going to match here, and this is the case of P5. So, P5 2 1s followed by 2 1s are taken care here and here. And now, for the 1 1 followed by 0 0, 1 1 followed by 0 1, what is the match? 1 1 followed by 1 0, 0 0 does not exist, even the P6 and P7 are not the cases. So, for these 2 cases we do not have that. What is the best match that I can have? 1 1 followed by, if the destination IP address is 1 1 followed by 0 0 and P4 is not the right match, P5 is also not the right match. What is the match that you can find out? Best match that you can find out is the P3, which is already there in the first level try. So, in order to that I am going to mark these as blank ones. So, there is no additional prefixes that are matched for using these set of the values. Whatever you found out in the first case itself is the best match that you have found out. Now, P length of 4 up to length 4 are taken care. So, P2 does not have, P2 is not the superset of any of the prefixes here. I am going to mark this as blank, this as blank, this as blank, and only P3 is a prefix of P4 and P5 that we note here, and similarly these two also will not have any expansions. Now the prefixes up to length 4 are taken care, and now there are prefixes which are greater than up length 4. So, which in this case is the P6 and P7 which are of length 6. I am going to write what is the if P4 is a prefix of something, if P5 is prefix of something, that I need to extend further. So, P6 is 11 followed by 11, which is we are right now here, and then followed by a 0 star. So, in order to do that, I am going to have pointer here and then construct another I and write all 4 possibilities 0 0 and 0 1, 1 0, 1 1. The pointer is pointing to this table, and what it says is it is of length 5. So, again you do the P6, if you expand, P6 will include what all 1 1 1 1 0, and I want a length of multiple of 2. So, this includes this, the 6th bit can be 0 or it can be 1 1 1 1 0 followed by 1 and then a star. So, these two cases. So, either the last bit 2 bit can be 0 0 or 0 1, these two cases P6 includes. So, I am going to write P6 here and P6 here, and this is the last we have. I am going to mark all of these pointers as blanks, and this is blank, this is blank, because 1 1 followed by 1 1 followed by 1 0 is the best match that you can find out is the P5 in this ample case. So, that is taken care, and similarly if P4 is a prefix of something else, so then again we need to accommodate that as well. So, in this case as P4 is 111 followed by 0, 111 followed by 0 is P7. So, I am going to have a table here, and then again the 4 cases 0 0, 0 1, 1 0 and 1 1, and this is again you do the expansion of P7. So, those 2 cases P7 would involve 111 followed by 0 and another 0 and then a star, 111 followed by 00 and then a 1 and then a star. So, 2 ones in the first level, 2 ones in the second level, and then followed by 1 0 in the second level and then 2 zeros. This is going to be with P7, and then 0 1, this is going to be also matched with the P7. These all pointers are, and the other is in this table are blanks. So, this is how I construct the bit trie. So, in effect what I am trying to say is you decide how many number of the bits so that I am going to match in one comparison. If your router, the processor that exists in the router is able to do multi-bit comparisons in one go, you actually said let's say I am going to do 3-bit comparison, I am going to do 2-bit, I am going to do 4 bits, 8 bits, whatever is possible. You do all of them, thereby you considerably reduce the height of the trie. So, I am going this you can think of the extension of the previous case. All that we did is formalize in every, instead of doing a variable number of the bit comparisons at every node in the previous case, all that I am saying is every possible node I take the fixed number of the bits and do a search in this table, and you can even hash it, and then in one reason you will going to get what is the corresponding node, and then you traverse this trie, and wherever you find a blank pointer, that is the best match that you can find for that particular destination IP address. So, for 2-bit multi-bit trie, this is the structure. So, I can also very well do it with the 3 bits as well. So, let us try to do that for the same set of the sequences, how the 3-bit trie would look like. So, if you do a bit trie, then what is the case? You are going to have 8 number of possibilities, and every reason I am going to do 3-bit comparison 0 1, 0 1 0 and 0 1 1, and the next one 1 0 0 and 1 0 1 1 1 0, and then finally 1 1 1. So, 8 possibilities are there. Again the table would have two parts, one first for the prefix and second one for the pointer, and then out of this you actually try to match what is the best possibility that you get. So, in the previous example, if you find a 0 0 0, that is best matched with P2, I am going to write a P2 here. If it is 0 0 followed by a 1, then also in this case the P2 is the best match, I am going to write here P2. And if it is 0 followed by a 1, then in among these set of the prefixes, what is the best match? Star is the best match you find. So, I am going to write P1 here. And if it is 0 followed by 1 1, then also star is the best match that you can find. So, then I am going to write P1 here. And 1 followed by 0 1 followed by 0, none of these prefixes are matched, then the best match that you can find is the default route, that is the P1. I write P1 here. 1 0 1 will also best match that you can find is the P1, then I am going to write here. 1 1 0 is best match. So, 1 1 followed by star is there, that is P3, and that can be 0. So, I am going to write P3 here. 1 1 0 is P3. And 1 1 followed by 1 is can also be matched with P3. I am going to write P3 here. So, these all cases will have the pointers as null, but only P3 is actually prefix of something else, that we understood. 0 0 is the none of the prefixes which are greater than length 3 are having the superset subsets of this P2 and even. So, I am going to omit that. So, these two cases are there. So, I am going to now have a second level structure. So, remember what is the longest prefix length we have got? 5. So, if I do a P3 bit comparison at a time, then the 6 is the next level. So, in 2 hierarchy level, I am going to be able to finish the entire comparison. The second level will have options from 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, and then 1 1 1. So, this is the prefix first column and then the pointer table. If IP address is 1 1 1 1 followed by 3 zeros. So, 1 1 followed by 0 0, P7 is the best match that you can find out among these set of the prefixes, and 1 1 followed by 0 1 is again the best match that you can find is P7. Similarly, this is going to be P4, this is going to be P4, this is going to be P6, this is going to be P6, and this is going to be P5, and this is going to be P5. So, the longest prefix that we have got is of length 5. So, we are at the level 2 and 3 bits at a time. So, 6 bit cases are taken care, and all of these actually pointers are having the null values. So, depending upon I decide to let us say I decide to match k bits at a time, and I have got 32 bits possibility, 32 divided by k, let us say that is 4, and then you need to expand what would be the height of the you need to construct this structure for up to length 8, 8, and then you will be able to find out the match. So, the larger the length of the match in one go, if I decide to do 16 bits, and then in only 2 levels I will be able to do the again, but that comes at the expense of the table size growing. So, you need to each level table will have 2 to the power of 16 entries. So, that is not desirable. So, there is a trade off, how many number of the bit comparison that you can do, and what would be the height of the total structure that you get. So, with that background in mind, let us try to understand what is the performance of this multi-bit trie, what advantage that it brings. So, one is the first thing is what is the node structure. So, I got a table in the place, and each table has got key number of the pointers and key number of the entries, 2 to the power of key number of the entries. So, at every level you will have got where k is the length of the match that you are going to do in one direction. In one go I am going to do the k bit matching. So, accordingly I can the data either the if you use a linked list, then you can create a structure which has got 2 to the power of key number of the entries and then those many number of the pointers, and that is one possibility. Or you can use the kind of the hash map or the algorithms where in order of 1 you can find out which actually prefixes 3, in this case k bits are matched, and then accordingly you can take the pointer. So, that is the alteration that is done. And in terms of the space, how much space you require, 2 to the power of key number of the entries in one table and then those many number of the pointers. So, the number of the entries, the size of the table, so which is 2 to the power of k. So, each node has got the 2 to the power of k number of the entries, which is going to accommodate all the possibilities in that structure. And the lookup operation is now speed up by k times. If w is the length, 32 bit IP address are there. In each iteration I am going to match 2 bits or 3 bits, 4 bits, whatever it is, and w, the total number of the memory references, the number of the pointers that you travel is reduced by k times, because every time you take one pointer you actually match k number of the bits, and the next when you go you again match the k number of the bits. So, w by k is the total number of the lookup operations that you do, and again as usual the update operations will also take w by k number of the times. In the worst case you traverse the entire w by k number of the tables, that is the height the tree, and then you are going to add a new entry in the table. So, that is the performance of this multi-bit trie. So, in effect let us summarize what is the optimization that we discussed. First we took the prefixes and then constructed the binary trie, which is actually doing 1 bit comparison at a time, and then in the worst case we said that for IP version 4 address you require 32 number of the memory references and the pointer references. So, that is going to be little slow. We tried to optimize that. We brought up another variant of the binary trie, which is path compressed tree, which is doing some kind of the variable number of the bit comparisons at every node depending upon whether the intermediate nodes are compressed or not. That we indicated usually by adding couple of variables inside the node structure, which is the segment length and the skip value. And then we went one step further and then said that instead of doing the variable number of the bit comparisons at every iteration, I am going to do a fixed number of the bit comparisons at every level. So, be it 2 bits, 3 bits or 4 bits. Then we said we came up with this data structure, which is the multi-bit trie. So, this is we argued that if your processor is able to support these k bit comparisons in one go, then the lookup speed is going to be k times faster than the binary trie's baseline performance. Although it is not exactly k times faster, but on average you will get the k times. Why it is not exact? Because multi-bit comparisons you also need to read that in one, when you visit in particular node, you need to find out what is the you need to read 3 bits of the input and then do a 3-bit comparison, which may not be exactly as much fast as the 1-bit reading and 1-bit comparison. So, but on an average you get k times the once improvement over the binary trie. So, with this we will stop at this point of time. In the next class we will see what are the other possibilities that exist. Are there any other optimization that I can do with the for the lookup operation.